Okay, thanks everyone for joining another Rocky in Action, our 15-minute learning session. My name is Vinicius. I'm part of the Rocky DEM support team, and today we are going to make a short presentation about dryers and how can Rocky DEM help you to actually model and get meaningful information for those type of equipment. So what is a dryer for? In very general lines, dryer basically is any sort of equipment that will ultimately reduce particle moisture. So basically, whenever you have a grain or any type of particle that contains moisture, for several reasons, you want to reduce the moisture content of those particles for storage or for better product quality and for any other reason. And this is when you require such equipment such as this one shown here in this right-hand side figure. And what do we actually expect from a dryer design? Basically, we want the grains to dry evenly as possible, so that you have grains as uniform as you can in the same amount of moisture. And also, of course, we cannot forget that it's very important that we have all this process happening in a cost-effectively manner. Okay, so we want to dry our grains, but we also want to do it saving as much money as we can. And of course, that the ultimate goal is to have grain moisture reaching the expected levels, okay, be it by regulations or for that type of for that specific type of product, you want a specific as well amount of moisture. But it's very important to reach those levels without getting damaged, okay? And how DEM simulations can help you with that? Basically, as any other equipment, we know that DEM simulations help us to get meaningful information on the particle level, and that can help us to have better equipment designs and also to tweak with operating conditions so that we reach those two goals I just mentioned in the best way we can. And if we reach this one here, of course, that we end up having better grains at the end of the process. In the end of the process, dryers can be found in many industries. For example, one of the most common one is probably the agriculture industry, where we have lots of restrictions, for example, on grain storage. So we know that moisture can bring a lot of problems when you are, for example, imagine you have a large silo and you fill it up with a lot of particles. And if those particles happen to be wet, of course you will favor microorganisms to build up, and this will end up damaging the whole product quality. Apart from that, we can also find dryers in the food industry. So one good example is, for example, when you have candies and you basically spray the sugar on top of those candies, and you want to dry that to create that nice layer of dry sugar on top of the candies. So basically you spray or you make the particles wet, and then you dry them for a while, and then you spray again, dry again. So we call that batch drying process. So those are found in the food industry. Also in the pharmaceutical industry, we can find dryers such as agitative filter dryers, in the chemical industries, and also in other industries. And another good example here is that whenever you cut off a tree, for example, you have your lumbers, they are wet, okay? And for several reasons, you don't want that wood to remain wet. One is because, of course, it is heavier when it is wet. So to save money when during transportation, you want to make those wood lumbers more wet. Okay, you want to reduce moisture in order to reduce weight. And of course that for a lot of industries, a dry wood is necessary, such as building furniture and those kinds of applications. We don't want our wood to bend or twist, so it's important to have a very well-controlled drying process. So in today's session, basically, we will be setting up a very simplified fluidized bed dryer, and then we will be post-processing it. And this is what you will basically learn today. You will learn how to import geometries actually using a Fluent case file, which is a very nice feature that Rocky has when you are doing company simulations, instead of loading STL or any other file type, supported file types. Also, we will learn how to set up the CFD coupled particle drying module, which is the module that will allow us to consider the drying process caused by a fluid flow. We will also learn how to define the particle initial moisture content, and also how to set up Fluent two-way coupled simulation, and then post-process the drying related quantities. Okay, so let me just switch to the screen. Okay, so this is basically Rocky 4.5.2. So I just started a new Rocky session. So as usual, we start by giving a name to this project. So just call it fluidized bed dryer. And then the customer name, let's give it ESSS. And this is fine for now. So moving on to the physics tab, one important thing regarding drying is that we turn on thermal modeling, okay? Because this will be necessary to compute the rate of evaporation of the particle. And we leave everything as default. We are not going to use coarse graining today. And we leave also momentum tab as default, and also the gravity tab we also leave as default. So for the modules, it's important that we turn on the CFD particle drying, and today we'll be also turning on Rocky's CFD coupling particle statistics. So for this one, we want to enable convective heat transfer, okay, because we will be comparing that during post-processing. And for the CFD coupled particle drying module, we have all those inputs, okay? So the first one is just the liquid density, okay? So since we are dealing with air-water vapor mixture, we just leave this density as the density of water. The liquid molar mass is the liquid molar mass of water as well, so we leave it as default. The solute mass fraction, so this input parameter is for when, for example, as I mentioned in the food industry, you have sugar in your mixture, and then of course that when this mixture dries, only the solvent will be drying out, and the solute will actually remain and be included in the particle mass. But here, since we are just removing water from the particles, we can eliminate this one, okay? The critical moisture content and equilibrium moisture content, these two parameters will actually define when does the drying regime transitions from a constant rate regime to a falling rate regime, okay? So this is what this guy will do. We will leave this one as 20%. So it means that if the particle moisture is above 20%, that moisture will be removed at a constant rate. But if the moisture content falls below this 20%, then it will get harder and harder to remove moisture from the particle. And then equilibrium moisture content, we leave it as 12%. Okay, this will be below that, the particle won't dry anymore. The air relative humidity, we will leave as 20%. And the drying start time, stop time, we leave as default. We just increase these two guys here to 1,000 seconds as well. Okay, so for geometries, we'll just import that Fluent case file, as I told you. So we just load here, and then we just have to save this guy, give it a name. I'll give fluidized bed dryer, save it. Okay, and you will see if we drag here that we have all the geometries we need included. Okay, so we don't need to load the STL files. Here we are going also to duplicate the inlet, so we create a support for the bed so it does not matches with the inlet of the geometry. You just give 25 here. Okay, and this is pretty much it for the geometries. So no motion frames for this case. For the particles, I have taken the properties for corn, for example, so 721 kilograms per cubic meter. Young's modulus, just use a lower value, and then 0.16 for the thermal conductivity, and 1954 for the specific heat. We are going to duplicate the boundary material. We're calling these guys symmetry, okay? Because this is just a slice of the fluidized bed, so we just create a new material so that we can give it zero friction between the particles and the boundaries. For our particle, we name it corn, and we give it a size of 5 millimeters, okay? And this is pretty much it. And we just need to set up the inputs. I'll use a volume fill for this one. I'll select the particle, select the mass I want to inject. And then, of course, it's important to set the initial temperature. So we just give it approximately 25 degrees Celsius. The moisture content. So this is how you set the initial moisture content of the particles, okay? So how wet will they be? We just say they will have 25% moisture content. And for the region, we check everything here, use geometries to compute, and select the seed point to 0.3 meters. This is it. Then everything that we need to do now is to load our Fluent case file. We use the same one we have used. And Rocky will undergo mesh validation process, which is very fast for this case, very small mesh. And as soon as we have it loaded, we just need to set up the drag law. We leave as default, and the convective heat transfer law. Let's choose Franz and Marshall for this example. And everything else we can leave as default as well. And I really like to use a -G argument so that Fluent runs in batch mode here and makes everything faster, okay? This is pretty much it. Now we just need to increase the time. For this example, I'll run it for 120 seconds with the output frequency of 0.05 seconds. And as soon as we hit start, the simulation will run, and we will get these results, as you guys can see here. So we have a very simple case. You can see particles mixing nicely. And what can we actually get from this simulation when we turn on the CFD coupled particle drying module? So basically, I have separated a few things I would like to show you. So one of them is that, of course, that we can color the fluid nodes by any fluid property or fluid scalar that we want. So you see that the fluid starts with 323 Kelvin, and particles start with 298 as we have set up. And as the simulation progresses, those two, the fluid and particles will actually exchange heat, and you see here the temperature field changing, okay? So what's nice to see here is that if we plot, if we plot the particle temperature, which is here, time plot, showing you time plot average. So you see the particle temperature actually topping up at approximately 302 Kelvin, which is actually the wet bulb temperature for these fluid conditions. And this is what should happen, okay? And this happens because, if you see, this happens because of this here. So basically, this is showing you the green curve is the heat loss due to evaporation, and the red curve is actually the heat received by the particle by convection. And you see that those two things, they match, okay? They reach a regime, they are balanced, and this is when you reach the wet bulb temperature. Also, another meaningful information here is that we can actually also check the rate of evaporation of the particles, okay? So this is one of the scalars you find here under the particle scalars, this one here. And with this one, you can, for example, predict how much time will you take to reach a certain moisture level, okay? And also, you can also see the most important, which is the particle moisture content. So this curve here shows you the average moisture content, which is decreasing with time, as we expect. This green one is the minimum moisture content, and this other one is the maximum moisture content. And you will see that those curves are actually getting away from each other, and that's why you see the standard deviation, which is this orange curve here, growing. And this is the COV at approximately 2%, okay? So this one can be used to see if particles for a certain time or for a certain batch duration, if particles will reach the expected moisture level. And a lot more can be done here using Rocky's features, but moisture content and rate of evaporation are definitely the two quantities you want to follow here in this simple example, okay? Okay, so what can we actually get from this simulation I just showed you? So using those results, we can definitely determine the proper dry media operating conditions. For example, you can change flow velocity, temperature, and humidity and see how those quantities will actually impact the dynamics of the system and the way the moisture content decreases with time. We can, using that information, we can determine the batch duration to reach the expected moisture level. And this is very important because grains cannot dry too much. They can be damaged by that. And also, if they dry too much and you are drying with a hot fluid, the temperature of the particles will increase, and you will end up also having problems because the grains cannot also reach too high temperatures. And using visual results, you can also prospect possible grain damage due to the factors I just mentioned, and then you can work changing the design or the operating conditions to tackle and to avoid those things, and also a lot more. We are having another session of the Rocky in Action, which will take place in December 15, okay? And this will be about coating. Please join us there. It will be a very nice one, and it will be related to this one as well. And if you want to hear more about the CFD coupled particle dry module, please stay tuned for our next webinar, which will take place in December 9, 2021. And this will be also bringing the details of this module, and then we will show also another application cases that you can run using this module. So this is it. Thanks a lot.